Well, good afternoon. This is at least 12:22, Wednesday afternoon, stormy day, 26th of September. And I'm wondering if the storms are why there's no students in here. Right now, I'm the only one in the classroom, supposed to be Cal 3. Let me just make a couple of announcements on the system so everybody can hear these. If you're graduating fall term and haven't applied to graduate already, you need to apply immediately, because we've gone to this term, it's the first term we've gone to 2 graduations a year, one at the end of fall and one at the end of spring. We've always had at the end of spring when everybody comes back to graduate. Now they're doing fall and spring, so some of the summer and fall people can graduate, can actually do the ceremony in the fall. And then spring is when more people probably will be doing it. But if you are going to graduate this fall, they have to have the information in like immediately. Okay, so please do that. If you're graduating in the spring, this is the best time to start the process, because the process involves getting a degree audit, and that's basically getting your degree plan, seeing what you have taken, what you haven't taken, what you need to take, and then see your advisor, and soon we'll be publishing the spring schedule, and you can see what you can take in the spring and if you'll be able to graduate in the spring. And if not, maybe you can get people to offer courses if you still need them that are not being offered, or see if you can do a course substitution if they're not going to be able to offer them. Okay, then after you do all that with your advisor, then you apply online. Okay, so please start that process now. Got to do it now if you're graduating in fall. Good time to start it right now if you're graduating in spring. Also, the other thing, I've announced these before, they're looking for note takers for this fall. Student services specialists are looking for those because they have some students, for either physical or some other reason, have trouble taking notes or need to have someone to help them. They will pay you to take notes. Our Office of Disability Services will pay you to take notes for students. Also, the Space Center is looking to hire peer tutors, that's you people, in the areas of math. There's no one any better in math than you are. English, biology, computer science, and Spanish. So check on both campuses for either of those 2 positions. All right. I thought if I waited long enough, someone would show up. I'm going to close the door because there's some noise in the hall. I'll be right back. Okay, sorry about that delay. This is where we left off last time. We were talking about tangent vectors and normal vectors, and the statement here says this also holds for curves in space. That is, for an object moving along a curve C in space, 3-dimensional curve, then the tangent vector, the t of t, and that's a unit vector, by the way, the tangent vector, unit tangent vector, points in the direction the object is moving. Whereas the normal vector, and that's a unit normal vector too, is orthogonal to the t of t and points in the direction in which the object is turning, okay, in the direction of the greatest amount of the turn, okay? And this figure here sort of shows that. I think I'll leave my pen sort of reddish, for now it'll show up better. Obviously the curve is coming this way and the object is moving that way. I know that because the tangent vector, unit tangent vector, is in this direction. If it was moving the other way, the unit tangent vector would have been in the opposite direction. Okay? The unit normal vector is this way. Now this happens to be a cylinder, okay, and following this curve, so everything's parallel to the z-axis, so the unit normal vector is pointing in the direction. It doesn't have a z component. Z component is fixed. It doesn't vary with z, okay? It's fixed at that point, okay? So any point on a curve, a unit normal vector is orthogonal to the unit tangent vector. The principal unit vector points in the direction in which the curve is turning. Now, if that had been a three-dimensional space, it's three-dimensional, but not a cylinder, had been, shaped some other way, it would be the component of that it's turning in perpendicular to the unit tangent vector. Okay, I guess that's the best way to say it. Okay, so looks like they're skipping example 4. So let's go back somewhere. I think this is the best I can do here. And let's do example 4. Now I'll get my color back. Finding the principal unit normal vector. Find the principal unit normal vector for the helix. Here is your r of t equal 2 cosine t in the I direction plus 2 sine t in the j direction plus tk. Okay. Now, it says find the principal normal vector. In order to do this, you got to come up with the tangent vector first, unit tangent vector. Well, the unit tangent vector is in the direction of the motion, or the velocity, which is going to be given by r prime of t. And what is r prime of t? Minus 2 sine of t, derivative of cosine is minus sine, in the I direction, plus 2 cosine t, because derivative of sine is cosine, that's in the j direction, plus k. Okay? Now that's r prime of t, for any value t. Okay? By the way, they don't give you a particular point here, so we're going to be finding the principal unit normal vector at any value t. So it's going to be not going to be a specific point where we're finding this. Well, the next thing we've got to do to find the unit tangent vector, that's the velocity vector, or the r prime vector, divided by the magnitude of the r prime vector. So the magnitude of the r prime vector is the square root of 4 sine squared t plus 4 cosine squared t plus 1. Okay? It's the square root of the sum of the squares of the component vectors. Okay? Well, 4 sine squared t plus 4 cosine squared t, if you separate those out and factor out the 4, that would give you 4 times sine squared plus cosine squared. That's 1, Pythagorean identity. So that would be square root of 4 plus 1 is the square root of 5. So what is our r prime of t? Our unit tangent vector. Okay? As a function of t, it is minus 2 sine t I plus 2 cosine tj plus k, all divided by root 5. Now you could put the root 5 under each component. That would be perfectly fine too. In fact, I kind of prefer it that way. So I think I'll go on and do that. Let me change this ever so slightly. So that will be reflected here over root 5 over root 5 over root 5. Okay? Now, next thing we've got to do is the first derivative of the unit tangent vector. Now, even though the tangent vector is a unit vector, its derivative is not, so I go back to putting an arrow over this one. And this is going to be minus 2 over root 5 cosine t I minus 2 over root 5 sine t j, and then none. There is no k component, z component of your first root of the unit tangent vector. So guess what? Not going to be one in the unit normal vector either. Okay? So what we do here, next thing we've got to do is take the magnitude of this, so the magnitude of this tangent vector, first root of the unit tangent vector, would be square root of 4/5 cosine squared t plus 4/5 sine squared t. Okay. And when you factor out the 4/5, you're left with cosine squared plus sine squared, which is 1. So that's the square root of that. So the unit normal vector, and this will be a unit vector, as a function of t, is going to be the tangent vector, the first root of the tangent vector divided by, let me go and finish doing this. This would be the square root of 4/5. Okay. Which is, the square root, so bothered by that stuff keeps flashing up there. Okay. 2 over root 5. Okay. That is the magnitude of that unit tangent vector. So what we're going to be doing is multiply or dividing this vector here by 2 over root 5. Well, look, dividing 2 over root 5 into those two, that'll just cancel out the coefficients. So you're left with minus cosine ti minus sine tj. Okay? Period. Okay, that's the T there. It doesn't look like it. My pen is moving really slowly today, or the marking is, so it's kind of hard to. I'm writing on the screen without seeing what I'm writing, so some things don't come out too clearly. All right. Well, we got to check and see if that is a unit vector. Cosine squared plus sine squared. Sure enough, it's 1. So that is a unit vector, and that would be the unit normal vector. Is always okay. Let's just take t equals 0. That would be in the minus I, pointed in the minus I direction. Well, if you look in your text, you'll see that when t is equal to 0, well, look at the r vector. When t is equal to 0, you're at 2I period, okay? 2I, okay? So that's out here on the, go out the x-axis 2 units, don't go y or z. Unit normal vector is pointing in the minus 1 direction, minus I direction. When you go over a little bit further along, always in a direction that has no z component, so it's pointing just straight toward the z-axis, not pointing up or down at all. And so it's always pointing toward the z-axis, directly toward it. If you squish this helix down, you know, and made it a circle, that's what you would get then, of radius 2, then all these would be pointing toward the center of the circle because your z-axis is the center of that helix. So there we have it, and that's hopefully about what you would expect. Okay? And they show it in the figure. That is what you get. All right, let's move on to have I gone too far? Let me see. No. Here we go. Tangential and normal components of acceleration. All right, in general, part of the acceleration, okay, if an object is moving in space, just picture a plane doing loop-de-loops, curling, do whatever it is in space, okay? Now, if it's accelerating, what makes up acceleration? First is a change of speed, okay? And that would be a change in the direction you're moving, either speeding up or slowing down in that direction you're moving. That is an acceleration, but any other change of direction is an acceleration as well. So you have two parts of your acceleration. That which is in the direction of your motion, in other words, in the direction of your velocity, that's the tangential component, because velocity is always tangent to the curve, the path that you're following. So that would be the tangential component, okay? So that would be the change of speed part, and then the change of direction part is always your normal part, okay? It acts perpendicular to the line of motion. In order to determine those two components, you use the unit vectors, t of t and n of t, to serve in much the same way you do I and j in representing vectors in a plane. Okay. And the reason for that is that you really do have a plane that describes that acceleration at any point. One dimension of the plane would be where the unit tangent vector is going, and then perpendicular to that, the unit normal vector, that defines a plane. Okay? So they, in many ways, act like the I and j. The following theorem states that the acceleration vector lies in the plane determined by n of t and t of t and n of t, unit tangent vector and the unit normal vector. So here's theorem 12.4. If r of t is the position vector of a smooth curve C. Now what do we mean by smooth curve? No gaps, no discontinuities in the curve, and more than, in addition to that, no holes in the curve, and even in addition to that, no points, cusps, angles, or other things like that. Smooth curve is changing direction gradually, continuously, no abrupt changes in its direction. Okay. So if r of t is the position vector in the smooth curve, and n of t exists, there is a normal vector. Okay. Now the times when it would not exist would be, where the say a straight line. You're moving in a straight line. That doesn't have a normal vector, or it would be undefined, because there is no curvature, so therefore it can't have a normal vector points in the direction of curvature, and there is none. So the n of t does exist. Then the acceleration vector a of t lies in the plane determined by the unit tangent vector and the unit normal vector. The coefficients of the unit tangent vector and the unit normal vector in the proof of theorem 12.4. Oh, okay, sorry, wasn't paying attention. And by the way, this theorem, and I can't remember if all your theorems are this way, I don't think so. I know definitions aren't. Let me just go back and find the previous theorem. Definition, theorem, yeah. Not all the theorems have that. I didn't think they did. This theorem happens to have one of those, goodness gracious, it's something like an RT code or something like that. The little square that has all the little dots and dashes in it, are pixels filled in and pixels not filled in. Also has three of its corners have little squares in them and one does not. I think this is called a QR code or RT code. It has some name like that. This theorem has it. So if you click on with your phone on that code, that box, okay, then you'll probably pull up, I'm guessing, the proof of this theorem. I'm not certain that's what you get, but that's what I'm guessing it'll be. It'll give you the proof, or at least part of the proof of the theorem. Try it, see what you get, okay? They do give you a portion of the proof here, so I guess this does it all. So you can look at this and see the bottom line being that the coefficients of the unit tangent vector and unit normal vector in this proof are called the tangential and normal components of the acceleration, and are denoted by this. The tangential component of the acceleration, exactly what I said before, it's the basically, well, not exactly what I said before, but it has to do with the speed, okay? The speed, yeah, it is exactly. It's the change, the acceleration due to a speed change, because the speed is the magnitude of the velocity vector, as you see there, and the first derivative of that is how that velocity vector is changing. In other words, how is the speed changing? Okay, that's the tangential component of the acceleration vector. And then you take that speed and multiply it by the, first derivative of the unit tangent vector, and that gives you the normal component. Well, let's see, why would that be the case? Well, we know, okay. All right. Let's go back a slide or two, or 3 or 4, okay. Somewhere back here. Here we go. Right there. The unit normal vector is the first root of the unit tangent vector times the magnitude of the unit tangent vector. Go back a few from that, and you have that the unit, well, there's that same one. Go back a few more, and you have that the unit tangent vector is r prime of t divided by the magnitude of r prime of t. R prime of t is just the velocity vector. I'm so glad to see you. I get so tired of talking to myself. So I'm glad you're here. All right. All right. Let me pause for a moment and first turn on the projector, and also switch my lights so you'll be able to see the projection better. Kind of miserable weather outside, isn't it?
Yes, I'm very wet. My car is acting up.
What you said?
My car was acting up. I said I'm very wet.
Oh, wow. Sorry.
I don't know where I'm going to get that.
Yeah. Okay. So the projector is coming on slowly. And I did make these announcements earlier. You're not real close to graduation, or are you?
I am.
You are. This term or next term?
Next term.
Next term. Have you already applied to graduate?
No.
No. It's a good idea to start that process now. You have time, but you don't want to, I mean, you can wait till the term you're graduating to apply. It's far better to apply the term before you graduate. Okay, and here's why. It's a 3-step process. Do a degree audit. In other words, get your degree plan. Look and see what you have taken and what you still need to take to complete your degree. Okay? And get with your advisor and go over and make sure you're understanding it right and he or she's understanding it. And then when spring schedule comes out, which will be coming out within the next couple of weeks, then you can check and see if you can sign up for the classes you need to graduate. Now, if you can't, you have plenty of time to get in touch with that department, if it's a different department from yours, and see if maybe they can add that class that you need to graduate to the schedule. Because we've got some flexibility now. If they can't, then you can see if we can do a course substitution to take some other course because you can't take the one that you're listed for. And if either of those things take time, if you wait till the term you're graduating to do it, you're almost out of luck. You know, if you can't do a sort, yeah. So it's good to do this before you apply, before you register for your last term. That's the bottom line. Okay. And then once you've seen the advisor, you've got lined up, then apply to graduate online. Okay. It's an online application. No more paper application. So do that as soon as you can. Well, you got a little bit of time because we don't even have the spring schedule yet. But within the next couple of weeks, start the process. Okay. Now, also the Office of Student Services is looking for. You heard these?
You are my advisor.
I am your advisor. You poor thing. You. My condolences. Okay. So get your degree plan. Make sure you understand it. Come and see me sometime, and we'll work through that.
Yes.
We don't have the spring schedule yet, so we can't do the final part, but we can at least get looking. And that way, if I know you need a certain class, I'll be sure to put it on the schedule, if I control that. Now, if it's chemistry or biology or something like that, computer science, I can't control those, but we can contact somebody and say, can you make sure you can get this on the schedule so you can graduate? Yeah. Okay. Now, Office of Student Services is looking for note takers. They obviously have someone with with some type of disability that they can't take notes themselves. They will pay you to take notes for them. So that's a possibility. Also, the Space Center is looking to hire, in other words, they'll pay you peer tutors in the areas of math. You'd be great in that. English, biology, computer science, or Spanish. So 2 possibilities. They are needing people to do, and they'll pay you to do it. Okay?
How much they pay?
What's that?
How much they pay for the 2?
They pay a little bit better than minimum wage is what my understanding is. I don't know how much better, but you see you're here already. You can set your hours pretty much. So, you know.
This campus or another campus?
Both of those people that made the request are from the other campus. But they may be needing people on this campus as well. Maybe they just did one flyer for both campuses. I don't know. They didn't specify. So, but a lot of times it'll be for either or. And if Dr. Hernan, who's in charge of the disability services, she's on this campus, so she'll know. So you can talk with her on this campus. Ms. Janine Jones is on the other campus, and she's who did the email. The Space Center, the person from the Space Center in Birmingham did the email, but we have a Space Center here as well. We also have student support services that uses peer tutors, so there might be another opportunity here. So give it a look. Okay, here's where we were last time. I mean, before you came in. I'll sort of start this slide over again. No, I'm sorry. This is not where I was. This is what I had just gone back to. I was pointing out to you that the unit tangent vector is the r prime divided by the magnitude of r prime. Now, when these vectors are dealing with actual position vectors, r prime is your velocity vector, and the magnitude of r prime is the speed. Okay, not a vector, because that's a magnitude. Well, hang on to that. We're talking now about velocities and accelerations, and the acceleration vector. This is the magnitude of the velocity vector. You don't have to put r prime of t. So hang on to that thought, okay? So here's where we were. We're going to combine it with, well, there was that vector again. Same thing I just had, okay? And why is I'm not finding this? And then here's the second one, which is dealing with the cursor, the unit tangent vector, and its magnitude. Okay, we can't do too much with that yet. Okay, let's move on. And there's that unit tangent vector again. I'm seeing it several times. Okay. All right, that's where I started today. You'll have to watch the video to get it. Okay? Did I miss that slide? Oh no, this was, I had to go back to write, find the slide to write on. We did this slide last time, okay? This is where we actually began today, but then there was an example that they didn't have on the slide set, so I went back and did it there. So here's what we're doing now, and this is what the acceleration vector is, and this is what we were just talking about. Well, close to it. Yeah, here it is. The coefficient vector, the acceleration component, the tangential component of the acceleration vector is merely that first derivative of your speed. Okay? Remember, acceleration can come from two things: changing speed or changing direction. Changing direction is an acceleration, changing speed is an acceleration. This is the changing the speed part. d by dt of the speed, the velocity vector, the magnitude of the velocity vector. That's the tangential component. Now the normal component involves that speed, but times the unit tangent vector, the first derivative, the magnitude of the first derivative of the unit tangent vector. And that's what I was trying to relate to. The unit normal vector is, this is the denominator for the unit normal vector. This is the denominator for the unit tangent vector, okay? And so basically, it's the speed, product of the speed times the magnitude of the change of the unit tangent vector, okay? And I can't think of a real good physically satisfying way to relate those two. This one relates perfectly, okay? That one, you just have to remember that's what they are, okay? It's the product of the speed and the magnitude of the change of the unit tangent vector. Just knowing that has to do with the normal vector, so that's the normal component of the acceleration vector. All right, and then that makes the total acceleration vector to be this component times in the direction of the unit tangent vector, plus that component in the direction of the unit normal vector, which always points toward the inside of the curve. Okay? Got it? Okay. The following theorem lists some of the convenient formulas for A of t and N of t. So A sub t and N sub t. Now remember, these are unit tangent vectors. It's the acceleration, the component of the acceleration in the direction of the unit tangent vector, and the component of the acceleration in the direction of the unit normal vector. Okay? So these tangential and normal components, if RT is the position vector, normally is, smooth curve, remember smooth curves mean no gaps, no discontinuities, no holes, smooth curve, no cusp, no corners, nothing like that, everything's smooth, gradually changing. The time rate of change of the curvature is continuous, okay? Now, and you have to have that the unit normal vector does exist. Now, where does the unit normal vector not exist? On a straight line motion, because there is no curvature there. So there is no unit normal vector for that. Okay. Then the tangential and normal components of that acceleration are as follows. This is easy. The first derivative of the speed. That's the acceleration in the direction of the motion. Okay? Now, two ways to get there. Either take this vector, take the derivative of that vector, and then take the magnitude of that derivative. That's what that is. Then take the derivative of that, and that gives you that component, the tangential component of that. Now that's a little hard, or at least awkward maybe. Another way to get it, if you know the acceleration vector up front, you've already known it, you calculate it. And that's easy to do. It's the second derivative of this. So go ahead and take the second derivative of this, and then dot product with the unit tangent vector. Well, to me, to get here, you had to do everything you did here. It's pretty easier to just do this. But if you're given this, then it's easy to do this. But then wait a minute. What is this? That is the velocity vector divided by the magnitude of the velocity vector. Well, wait a minute. Then this is pretty easy. Take the first derivative of this, that gives you this. Find its magnitude, that gives you that. And then take the second derivative of that, that gives you this. There you have it. The dot product of the velocity times acceleration divided by the magnitude, the speed, magnitude of the velocity. That's a pretty easy one to do. The component of the acceleration vector in the normal direction, remember that is this thing, the speed, the magnitude of the velocity vector, times the magnitude of the first derivative of the unit tangent vector, which is kind of a hard thing to get sometimes, which is, by the way, the acceleration vector, which is easy to get, second derivative of this, dot the normal vector. Well, hey, that's harder to get than this, okay? But if you go back and check, that is the cross product of the velocity and the acceleration vector, magnitude of that divided by the magnitude of the velocity vector. Okay? Well, why is that? Well, think about this then. The unit normal vector is this thing divided, I'm sorry. And it's not all that particularly easy to, again, the rationale for this is not an intuitively obvious one. But the form is pretty easy. The tangential component is the dot product over the velocity vector, the speed vector, not the vector, the magnitude of the velocity vector. Normal component is the magnitude of the cross product over that same thing. So just dot product for the tangential, cross product for normal, only you have to take a magnitude here because these are scalar quantities, so you can't have a vector in them. But even easier than that, if you've already done the acceleration vector, find its magnitude, and the square root of that squared minus this one, which you've already calculated, that will give you this one. So if you've already done the work to get this one, which is not that bad, velocity vector divided with the acceleration vector divided by the magnitude of that velocity vector, there's that, okay? Then you've already calculated this, find its magnitude, square it, then subtract from it the square of this thing, take the square root of that difference, and you've got this one. So that's usually the easier one to do. If you know the other things, that's usually easier. Otherwise, just take the cross product. And that's pretty easy too. Then do its magnitude. Note that the unit normal vector is always greater than or equal to 0. Why is that? This is the principal square root. Always greater than or equal to 0. This is a magnitude, always greater than or equal to 0. That's a magnitude, always greater than or equal to 0. So the normal component of the acceleration vector is always positive. The normal component of acceleration is also called the centripetal component of the acceleration, and because that's what's pulling it around. That's centripetal force is what creates the change, the curvature. Otherwise, it wouldn't curve if there wasn't a force there. Okay. So, here's example 5. Find the tangential and normal components of acceleration for the position vector given by r of t is equal to 3ti minus tj plus t squared k. Okay? Let me make sure I'm in the right place in the book. Yeah. There's example 5. And by the way, this example is given at larsoncalculus.com. You can see an interactive version of this type of example. It may not be exactly this one, but this type. Okay? Now, how would you begin? Say again? Find what?
The magnitude of the first.
Not of r. You don't need the magnitude of r. You need the magnitude of the velocity and possibly the acceleration. Definitely need the magnitude of velocity. How do you get velocity? Say again? Not yet. You got to get it first. Okay? You're saying the dot product V dot A, right?
Yes.
You got to get V. What is V? It's the first derivative of that. Your position, first derivative of that is velocity. Second derivative of it is the acceleration. Have you had physics yet?
Yes.
Okay. You know that's true, right? Okay. So the first thing you do, take a derivative. R prime of t, which, by the way, is v of t, the velocity vector. Okay? And what would that be? 3i minus j
plus
2tk. Perfect. Okay? That's one thing you need, the velocity vector. Okay? And while we're at it, let's go on and get the acceleration vector. Okay? Which is the first derivative of the velocity vector, which is the second derivative of the displacement vector. Okay? Which is what? Nope. Derivative of 3 is 0. Derivative of minus 1 is 0. Derivative of 2t is 2k. Not 2t, 2k. Derivative of 2t is 2. That is your acceleration vector, 2k. That's all, folks, just 2k. All right, now, it said the tangential, and we'll first do the tangential component. Okay, and you just were saying to me what it is. It's the dot product of velocity vector times the acceleration vector. So let's do that dot product and see what we get. V of t dotted with A of t is equal to what? 3 times 0 is? 0. Negative 1 times 0 is? And 2t times 2 would be 4t. Well, 4t. Okay, you don't carry the vector with it because it's a scalar quantity. Okay, 4t. Okay? So that is your, okay, that's the start of it. What do we divide that by? Magnitude of velocity vector. So here's the velocity vector. Let's do its magnitude. The magnitude of velocity vector is equal to the square root of, you square each component, 9 plus 1 plus 4t squared, right? Which would be the square root of 10 plus 4t squared. Okay? So, your tangential component of your velocity of your acceleration vector then would be the dot product of velocity times acceleration, which is 4t, divided by the square root of 10 plus 4t squared. Okay? That's your, goodness, my back is just like crazy. Okay. And that's your tangential component of your acceleration vector. Now, which way to do the normal component of that. There's two ways. If you, okay, I'll let you, are you finished writing? Okay, I'll let you finish. Okay. Okay. Two ways to do this. One, take the cross product of those same two vectors, its magnitude, and then divide by that same magnitude that we've already calculated. Okay, so that's going to be pretty easy. Or take the total acceleration that we've already calculated, find this magnitude, square it, subtract from it this thing squared that we just did, and then take a square root of it. So, which way you want to go? This way or that way? It's sort of up to you. In fact, we'll do them both ways if you want to. Huh? You want to do the square root way? Okay. If we're going to do it that way, then what we have to do, and it's not hard, okay, is we need to do the magnitude of the acceleration vector. Okay? Whereas here's the acceleration vector, it's just 2k, so what's its magnitude? 2, okay. That wasn't hard, was it? Okay? Now, the other thing we have to do, let's go back. There's the magnitude of that, we're going to square that, and then we're going to subtract from that the tangential component squared. Okay? So, the acceleration, the normal component of the acceleration vector will be the square root of this thing squared, which is 4, minus this thing squared, which is 16t squared over 10 plus 4t squared. Because when you square a square root, you just get the thing that's left. Okay? Now, this will be for any time t, so that's kind of an awkward form there. So what we're going to do is multiply, is get these over the same denominator. So that will be the square root of 40 plus 16t squared minus 16t squared over 10 plus 4t squared. Okay, which, looky here, the 16t squares go out, and we're left with the square root of 40, which is 2 times root 10, divided by, yuck. Let me erase this slightly and rewrite what I was going to do. Take out a 2, and then you have the square root of 10 over 10 plus 4t squared. Okay? So that's the normal component in terms of t. Okay? So it's 2, well, I thought they were going to go back. So I'm going to write it the same way I started to write it before, is 2 root 10 over the square root of 10 plus 4t squared. That's how I was going to write it. I thought, no, they're probably going to put it over the same square root. They didn't. They did it like that. So it's perfectly fine. So there's the normal component. As a function of time, plug in any time you want, and you can get the acceleration vector tangential component, and it's normal component. Okay. And you already know what the total acceleration vector is. All right, any questions? None? Okay. All right. Let's see how they do it. if it's any differently from the way we did. All right. Begin by finding the velocity, speed, and acceleration. Okay, velocity is the first derivative of that, which is exactly what we got, right? The speed is the square root of the magnitude squared, which is 10 plus 4t squared. Exactly what we got. The acceleration vector is the velocity, the first derivative of the velocity vector, second derivative of the displacement vector, which would be 0I, 0j plus 2k. Done. That's your acceleration vector. Okay. Okay. Now, they did it the acceleration, they did it the same way we did the acceleration component. I thought we had already done it. I guess not. Okay, the acceleration, the tangential component of the acceleration vector is the v dot a over magnitude of v. We calculated v, we calculated a, you did a dot product and got 4t, and we've calculated the speed, which is the square root of 10 plus 4t squared. So yeah, that was just easy, just plug and chug. Now, they did it the other way. They did V cross A. And I was real tempted to do it, but we're now doing it this way. To do a cross product, we do I, J, K, and we do the determinant form here. And the velocity vector was 3I minus J plus 2tk. So those are the components of it. The acceleration vector was 0I plus 0k plus 2k. 0j plus 2k. So it's this. Now, to do the cross product, I hope it's pretty obvious that this is the only one that gives us, maybe it's not obvious. Let's just do the rest of this. Repeat the I and the j, the 3 and the -1, and the 0 and the 0, okay? Do the downstrokes and you get minus 2i. 0, 0 plus 0j plus 0k. Then do the upstrokes. 0i at 0k, 0i, and that's a minus 6j. What's that?
Plus 6.
No, when you do the upstroke, that's always it's a negative. Okay, minus 6j. So that's your cross product of these two. And we're going to take that and divide it by the magnitude of v, which we've already calculated would be that thing there. So that gives us, we got to do the magnitude of this. Remember, that's a vector. This thing's going to be a scalar, so we have to do this magnitude. So what's that magnitude? The magnitude of this is in the magnitude of that, which is the square root of 4 plus, square this one, square that one. You sum of the squares.
Okay, I was saying that, because I was in 2 square, I was right.
Yeah, okay, sorry. Huh?
6 square
is 36. And that's the square root of 40. Looks kind of familiar, doesn't it? Okay? So then, what you do, you take that, the square root of 40, so your a sub n is going to be, the numerator is the magnitude of that divided by the denominator, which was just this, the square root of 10 plus 4t squared. Same v that we use there, just the denominator, right? Okay? and then this becomes 2 root 10 divided by square root of 10 plus 4t squared, which is exactly what we got before. Okay? So let's close this out. And that gave us minus 2i minus 6j. Normal component of that then would be this magnitude of that divided by the velocity vector, the magnitude of the velocity vector, the speed. That'd be square root of 4 plus 36 over square root of 10 plus 4t squared. It'd be 40, which is 2 root 10 over that. That's the normal component of the acceleration. Okay. Whoa. So that's it for example 5. And again, that's at larsoncalculus.com if you want to see that also done. They skipped example 6, 7, 6 and 7. You want to go and do those? Whoops. Boy, that doesn't leave us a lot of room to write. Let's write it here. Example 6. Find the tangential and normal components of acceleration for the helix given by r of t. They love helix, don't they? Okay. B cosine t I plus b sine t j. Okay. Goodness. I'm having trouble focusing my eyes, so my lettering is coming out really awful. Okay. That's pathetic. Okay. Plus CTK. All right. There's your position vector. It says find the tangential and normal components of acceleration for the helix indicated there. What's the first thing we're going to do? Second, take a derivative. And that will give us our velocity vector as a function of t is going to be your r prime as a function of t. Okay, and that's going to be what? Negative, second, negative b times the sine of t, I. Right? Okay, next. Okay, I can't hear well, sorry. And my pen, second? No, that's a plus there. Plus b cosine t j. Plus ct. No, c, not t, ck. Is that what you said? I can't hear well, so. The derivative of ct is just c, and that's times the component in the direction of k. All right. I'll try to stick through this to the end. I think I'm going to have to go get something to drink. I crammed down my salad and my sandwich. I didn't drink very much, so now I'm getting so dry in my throat and head that I can hardly maintain continuity. So let's see what we can do. All right, what do we do with that velocity vector? Yes, let's go on and do the acceleration vector as a function of time, which is also the first derivative of the velocity vector, which is the second derivative of the displacement vector. And what would that be? minus b times the cosine of t. Is that what you said? That's in the I direction.
Plus
Minus
b sine, right?
Yeah, it's a sine. My writing stinks. I was waiting for you to say something and didn't realize my pen was touching the page. Sine tj and
K?
no, that's a constant.
Oh, E.
No, that's a c, but it doesn't matter what it is. Yeah. I'll write that a little clearer. It doesn't matter what it is. It's a constant, and the derivative of a constant is 0. Okay, so there is no k component. Just sort of like what we've done before. Okay, now what do we do with those two initial pieces of information? And again, we want the tangential and normal components of the acceleration. So it's asking for the same thing that example 5 is asking for. It's just a different position vector. Okay, I'm sorry, my hearing's so bad.
Get the dot product of the velocity vector.
Yes, okay, let's do the dot product of those two. So V dot A, what would that be?
We set up that IJK formation.
Okay,
IJK formation.
we don't use I's and J's anymore. And by the way, I just noticed my first I here looks a lot like a J. Okay, I'm sorry. That's an I. Okay. We just multiply the I components together because dot product is a scalar number. So that would be b squared sine t cosine t minus b squared sine t sine t, and then there would be no k component, k contribution, because c times 0 is 0. All right, so what does this come up being? 0. No. Yes, it is. Can it be? Yes, it can. Okay? The tangential component is 0. All right, now what does that mean? It means this thing is not speeding up or slowing down, either one. It's traveling at a constant speed. So the tangential component is 0. Okay? So you don't have to do, well, you sort of do have to do the rest of it. What would have been the next thing we would have had to do for our tangential component? Yes, exactly. So let's go on and do that since we're doing it, even though we don't really need it for this part of the problem, we'll need it for the other part. What would that be? Square root of? Okay, it's a b squared sine squared t plus b squared cosine squared t plus c squared. Okay, it's the product of those components, square of each of the components. Sum of those taking the square root of it. Well, again, like we've done before, you can group these two together. and they both have a b squared in them, so factor that out. So this will be the square root of b squared, and then it's what sine squared theta plus cosine squared theta? Second? No. Sine squared plus cosine squared is? 1. 1 and only 1, always 1. Remember that one, that's really. So that's just 1. So you got square root of b squared plus c squared. What's that?
That was the simple. I forgot.
Yes, that's a very important one. Okay. So you get, that gives you b squared plus c squared. That's the magnitude of the velocity vector. Okay? Now, we've already gotten, this is also the tangential component of your acceleration vector is 0. Okay? Now, which direction you want to go to get the normal component of your acceleration vector? Okay, a little up.
Divide the absolute value of the cross product of v and a and the velocity vector and the
Okay.
acceleration vector.
Okay, so you're going to go back and do the cross product of those two,
Yes.
not the way you did it last time.
Yes. The way they did it.
Right, you're going to want to do it the way they did.
Yes.
Okay. Now, in this case, I like your first method better because guess what? The tangential component of your, tangential component of your acceleration vector is 0. So that means the normal component is merely the magnitude of your acceleration. Right?
Yes.
Oh, remember the second way? It's the square root of magnitude of a squared minus the magnitude of this squared. Well, the magnitude of this is square root of 0. So it's just the magnitude of a. So all you have to do is do the magnitude of this, and you got it. Because the tangential component is 0, the normal component is the same as a. So, don't you want to go that way?
Yes.
Yeah, I think so. The other way is doable, of course, okay? But this is so much easier, okay? So what we're going to do is we need to know the magnitude of the acceleration vector, and that's going to be the square root of b squared, if I could write, cosine squared t, right, plus b squared sine squared t, right? And that's just simply going to be factor out of b squared. And what's cosine squared t plus sine squared t? Please remember that one. What? That's just 1. So this is square root of b squared, which is b. Okay? And that's also the, whoops, not a vector, the normal component of the acceleration vector. That's it, because the tangential component was 0. Okay? Now let's see. I've lost which problem we were doing. That was the A problem, wasn't it? I mean, the problem 6. Yes. Yeah, and they went back and did this method. And that just gave them B. Do you see why? Tangential component is 0, so all the acceleration is in the normal component. Meaning it's traveling in a circle, okay? And there is no, it's not speeding up any. It's traveling at a constant speed in a circle, so therefore the tangential component is 0, so all your component is centripetal toward the center. All of it. Okay. Now, I keep looking at example 7 saying, how do they get that? Well, I'm looking at the wrong example. But now it's time to look at example 7. Right? Do you need any more on this one?
No.
Okay. All right. Well, oh, I'll put it in my pocket. I broke a pin on my watch and I can't find one to fit it, so I have to carry it around in my pocket. Okay. All right. Got time. All right. Now we do example 7. Okay. There we go. All right, the position vector for the projectile shown in figure 227. You don't have your book, do you? Well, we really don't need the picture. You can look at it if you want to, but I'll give you the position vector. R of t is equal to 50. I really don't like the way they write this. The book always does it. I'm going to write it the way they do. 50 root 2 t I. Now I made a special emphasis that closing out the root 2, so you don't think the t is under the root 2. My preferred way of writing that would be 50t times root 2. Okay, yeah, it gets out of order, but you're not at all about to confuse the t being under the house or not under the house. But they do it this way, so I'll try to do it that way so you, if that's how you see it, you understand it. That's the I component plus 50 root 2t minus 16t squared j component. All right. Now this is a plane curve, okay, not a three-dimensional curve, just x and y. It says find the tangential components of the acceleration at 3 different times. Tangential only. Not asking for the others. Okay? So what you reckon we'll do first? Take the derivative of your first, of your, this, which by the way is your velocity vector. I can't write, okay? Goodness gracious, I'm having trouble writing. And what is that? Second? No, it's 50 root 2, right? That's the coefficient of t. Take the derivative of that, t to the first power, times that, times t to the 0 power.
So okay, 50 wouldn't be considered as a constant.
50 and root 2 are both constants. T is your variable.
So the derivative of the constant is 0.
Okay. This is the same as equivalent to 85t or 67t, or, I mean, it's just a number times t.
Yes, so what the derivative of the constant is 0, right?
Say again?
The derivative of the constant is 0, right?
Okay.
So, and if 50 is a constant,
Right.
so that means 0, right?
Okay. But you're not, it's not 50i. It's 50 root 2t. Just some constant. Let's call it k. kt. What's the derivative of kt?
It's k.
K. There's your k. Right? Okay. So it's 50 root 2i. Okay. Plus, and this will have 2 parts. First part is 50 root 2. Second part is?
Plus 2t.
Second?
2t.
minus
minus 2t.
32t. Is that what you were saying?
Yes.
Yeah, okay, I couldn't hear.
2 times 16.
3 times 16, 32t j. Perfect. Okay? Okay? Find the position. No, position is that. Find the tangential components of the acceleration when at these various times. Okay? So we'll also need, what else?
What they're asking about?
The
What
what?
are they asking about again?
Okay? All we're looking for is the tangential component of the acceleration.
So we need the velocity. No, we got the velocity.
We got the velocity.
So we need the acceleration vector.
Acceleration vector. The acceleration vector is a function of time. It's the first derivative of the velocity vector as a function of time, which is the second derivative of the displacement vector as a function of time. And what would that be?
I is 0
Yeah, I is 0, so I won't even write that down.
and plus 32.
Only it's minus 32.
Minus 32.
J. Perfect. Now that makes you think that's the acceleration due to gravity, doesn't it? But it doesn't have to be, okay? But sort of makes you think that, doesn't it? Okay. Now, what next?
Now we do the cross product.
Okay, we're going to do the dot product at some point of V dot A. And what's that going to be? Kind of a big, ugly, nasty number, but it's just merely multiplying this times that, which will be a minus 160 root 2 plus whatever 32 squared is. I'm just going to leave it as 32 squared t. Okay? That's V dot A. It's this times that.
It's going to be 1024.
1024?
Yes.
That sounds reasonable. It's 1 meg, by the way, right? 1024. Okay. T. Okay? We need one more thing to get the tangential component of the acceleration vector.
What we need?
It's V dot A over, but
the absolute value of V.
the magnitude of V. Magnitude of your velocity vector. And so we have to calculate that, but that is the square root of, okay, 50 squared is 2,500, right? Times 2, because root 2 squared is 2, so that would be 5,000, right? Plus, okay, this will have a 5,000 in it because that's squared again, minus twice the product of those, which would be 16, huh?
It's 1024 because we had it right there. We had the square root of 32 right there. We did it earlier. The square root of 32.
Yeah,
So we have it again. It's
yeah. But we're not doing the square root yet. We did this squared for this one, plus twice the product of that. The product of this times this. I don't think we did that one yet, did we? We did something similar to it here, and it gives us a similar number, but it has more zeros after it. 1, 6, 0, 0. So it's 1600, isn't it? But we double it, and that's 3,200, right? Okay. So 3,200 T plus 1024 T squared, right? Now let me make sure I did that right. Whoops. Wait, I don't think I did enough. No, I left off a root 2. Didn't I? I'm getting really confused. No, I did leave off a root 2. Okay. So this one squared, and that squared is 2500 times 2 is 5,000, same as it was here. Okay. Minus twice the product of these two. So you have a root 2 in there. This times this is 1,600. Twice that is 3,200 T. And then plus this thing squared, which we had already done, would be plus 2,400 T squared. Okay? Whew. All right, so that is the square root of 10,000 minus 3,200 root 2 times T plus 1024 T squared. All right. Oh, wait, yeah, what a nice number. One of my favorites. Okay. So we take this thing divided by that thing, okay? And so your tangential component of your acceleration vector is that mess, okay? Minus 160 root 2 plus 1024 T over the square root of 10,000 minus 3,200 root 2 T plus 1024 T squared. Okay. Now, they want those at 3 different times. Yuck. The first time is T equals 0. That's not going to be too bad. So, A, the tangential component of your acceleration at time T equals 0 is going to be minus 160 root 2 over the square root of 10,000 is 100. So this will be minus 1.6 root 2, I believe. No. Yes, negative. No, they say negative 16. Well, let's see. Maybe I did it wrong. Did I drop a 0 somewhere? I must have dropped a 0 somewhere. And you may have been right. That's what I should have been getting before. I am sort of lost. Yeah, that was 2 zeros there. So this is two zeros here, and that's 2 zeros there. So that negative 116 root 2. negative 16 root 2, which is minus 22.6. Okay. I dropped. You're right. That should have been the same number as before. Okay. Now, that component at time t equal 1, all right, yuck. That would be minus 1600 root 2 plus 1024 times 1. So whatever that turns out being, and your denominator is 10,000 minus 3,200 root 2 plus 1,024. And they come out being minus 15.4. Now, I don't have a calculator, so I can't check them on it, but it looks like that's about right. Minus, that would be same as before. 1600 root 2 minus 32 minus and let's see, it looks like it comes out the same, so I'm not going to do all that math. Now let's see the last one. Bizarre number, 25 root 2 over 16. If you plug that in for t, this becomes a 25 root 2 over 16. Well, you know that 16 will go into this 16 times, okay? And 16 times 25 root t is exactly, root 2 is exactly that, so it's plus minus, and that's equals to 0. Strange time, but okay. So it seems like your acceleration is decreasing until it reaches 0 at that time t. So if you looked at the projectile motion that was describing, you don't have your book, so taking their word for it here, see, time t equals 0, there was your component. T equal 1, it's reduced a little bit, and that time, weird time there, that's where your tangent vector is 0. So your speed is exactly 0, and I bet you after that it's going downhill. Now, I can't swear that's going to be a parabola, but it sure looks like it could be. Okay? Have we run out of time? Yes, we have, basically. Okay? But we did finish the section 12.4. Homework exercises, do any of the odds 3 through 7. They're all at Calc Chat. 5's at Calc View. Do any of the odds 9 through 13. They're all at Calc Chat. 9's at Calc View. Do any of the odds 15 to 19. They're all at Calc Chat. 15's at Calc View. Do either 21 or 23. They're both at Calc Chat. Do any of the odds 25 to 29. They're all at Calc Chat. 27's at Calc View. Do either 31 or 33. They're both at Calc Chat. Do any of the odds 35 to 39. They're all at Calc Chat. 35's at Calc View. There is a number 41 that's sort of a talk-through type problem. It should be at Calc Chat. It may not be, but try it and see. Then do either 43 or 45. They're both should be at Calc Chat. Then do, and this is something that kind of aggravates me about this author. I've had several of his books before, and he does this in some of them. The last two books I've taught from, he does this. Here he's talking about the binormal vector. Well, we didn't cover that anywhere in 12.4, but he's given it to you in the homework exercises, okay, in the exercises. So he gives a definition and then asks you to calculate. So it's not...
Addition, so it's a mistake that they did.
What's that?
Maybe I think it's because of the new addition, so they forgot to remove that question from another chapter.
No, it's a bunch of questions. It's 47 to 51. No, it's intentional. He did it in the other text, the linear algebra text he wrote too. He'll talk along, do things, and then in the problem set come up with a new concept and said, now do this. Which is fine, but why not introduce it in the section and then have you do problems? But he gives you what it is, and it's a simple step, but do any of the odds 47 to 51, they're all at Calc Chat. Do either 53 or 55, they're both at Calc Chat. Do 57 or 59. I'll say any of the odds, 57 through 63, they should all be at Calc Chat. Do either 65 or 67, they're both at Calc Chat. There's a true false, 69, it should be at Calc Chat. And then there's a 71, it's a motion of a particle. That's a hyperbolic. I don't really care for that. You can do it if you want to. And then 73 and 75 are both proofs, so you can do those if you want to. We'll begin next time in 12.5, arc length and curvature. Okay, and let's see how much further we got to do in 12. I think that's it. So after we finish 12.5 will be test time for chapter 12. And I'll try to, I don't know if I'm going to have that done by Monday or not. It might be Wednesday before I have that test ready for you, because I've got a bunch of tests to make up. I'll see if I can get it done. Okay. Good deal.
Thank you.
All righty. Thanks for coming.